Good morning. I decided to use this to be quiet time as an exercise time. So from the next time on, I want to present some exercises in the beginning of the class. So when you sit here, then sit in a chair, then please solve some of the problems, okay? And until the class is ready to start the class, okay? So, just as usual, I present from this thing. So we will have a quiz next Wednesday, okay? So Monday, we don't have no class. We don't have any class. So Wednesday will be the next quiz, okay? Quiz 3. And if you want to resubmit or you want to submit as a late submission, please submit your quiz 2 on January 13th, next quiz, at the next quiz. Okay, and the solution is already posted in Moodle, and lots of information are in the Moodle. Okay, and we also provide some study resources, and I hope that these will be useful. And also in the Moodle, you can find the responses to the comment sheet. Okay, so as you ask some questions on the comment sheet, I will answer to your question. Sometimes it takes time, but anyhow, before the next class, I post the response to the comment sheet. Okay, and also you can use the Moodle forum called comments and questions. Okay, so if you post questions when you are studying by yourself, then just post your questions on the news forum in the Moodle site. Then in that way, I can respond to that question to all members of this class. Okay, and I think you may just want to ask me questions, but in many cases, lots of other students also have similar questions. So that's a benefit to other students as well. Okay, and the paper is due on February 9th, and I've already announced it a couple of times, so I just want to skip this one. And also the examples of the topic, since these slides are also posted in a Moodle, so you can check if you want to read it carefully. Okay, and this is the problem I just posted this morning. Okay, and in the first 3 we have already done in the I think December 21st or so. Okay, so I hope you have already done at least the top three problems. Okay, then this is the solution. Okay, if you look at the first one, then if you multiply a matrix to a vector, you will come up with Cx plus D. Okay, but important thing is, okay, please look at the right hand side. Then xyz became xy cx plus z, right? If you multiply this particular matrix, okay? But if you multiply this matrix, then the result you got is xy cx plus z, okay? But that is the same result as you apply an elementary row operation called 3-1c. Okay, replace the third row by the sum of the third row and the c times the first row. Okay, so that is cx plus z, right? So by this multiplication of this particular matrix, okay, that has the same effect as we apply the elementary row operation 3-1c to this vector. Do you understand what I mean? Okay. But if you look at this particular matrix here, okay, this has C at 3, 1 entry, a 3-1 entry. 3-1 entry means the third row and first column. Okay? So this 3-1 has to do with the location of this C. Okay? But anyhow, I will name it later. But if you multiply this matrix to this vector, this does the same thing as you apply this operation 3-1C, semicolon C, to this vector. Okay? Similarly, if you multiply this matrix to XYZ, the result becomes XYCZ. Okay? That is, the third row, in this case Z, is multiplied by C. Okay? So this is the same effect as you apply the row operation 3 semicolon C. Okay? This is to replace the third row by the C times the third row. Okay? That is CZ in this case. Okay? And then similarly, this one is, if you multiply this matrix to this vector, you switch or interchange the first row and the second row. Okay? And this is the same one as you apply this elementary operation 1, 2 to this vector. Okay? So in this way, there is some correspondence between the matrix operation and elementary row operation. Okay? So today we want to use this thing to understand the inverse of matrices and other important facts in linear algebra. Okay? But this is the next problem I showed in the bottom, at the bottom of the exercise sheet. Okay? The first one, first matrix here, is just the same as this one. Okay? So, which did the same effect as 3-1C. Okay? And then this one is the third matrix. Okay? And just multiply these. Okay? Then it may take time, okay, for you. But you already know that if you multiply this matrix, this particular matrix from the left, okay, then in each column, this does the same thing as you apply elementary operation called 3-1 semicolon C. Okay? As we have seen here. That means instead of just calculating the product of these two matrices, okay, in order to get the result, you can just use this operation 3-1C to get the result. Let's think about it. Okay, here, if you apply 3-1C, that is, replace the third row by the sum of the third row with the C times the first row. Okay, then C times the first row is 0C0, right? So if you add this 0C0 to the third row, it becomes 0C1. Okay? But if you multiply these two matrices, you can get the same matrix. Okay? Because if you multiply this particular very simple matrix from the left, okay, which is called the elementary matrix, we will introduce it later. Okay? But if you multiply this matrix, then since this does the same thing as you do the elementary operation called 3-1C, so instead of just calculating the matrix product, you can just do the same operation 3-1C to this matrix, then you can get the same operation, the same matrix. Okay? Then what about the next one? In this particular case, you multiply this particular matrix from left. Okay? And multiplying this matrix does the same thing as you apply, since we are multiplying this matrix, okay? This does the same effect as you apply this elementary operation 1, 2 to each column. Okay? So, in this case, if you multiply this matrix, then that means you just apply elementary row operation 1, 2 to this matrix. Then this matrix, okay, as you use this 1, 2 operation, then that means interchanging the first row with the second row. Okay? Then second row is 0, 1, 0, and the first row is 1, 0, 0. So the result becomes this. And this is nothing but the result you obtain by just the product of these two matrices. Okay? This is the important topic we want to study today. Okay? But another important thing as we look at this example is that if you look at these two matrices, they are a little bit different. Okay? I didn't make any miscalculation. The first row and second row are just the same, but the third row of the first matrix is 0, C1, and the third row of the second matrix is C01. So these two matrices are not equal. Okay? But look at the calculation we did. Okay? We multiply these two matrices. Okay? And here we multiply these two matrices, but just interchange the order. Okay? Change the order. Okay? So this matrix times this matrix, and this comes here, and this comes here. We change the order of operation. Okay? Then we obtained the different matrix. Okay? So in matrix operation, if you change the order, you may, okay, sometimes you get the same solution, but you may get a different solution. Okay? And on the screen, another sub-screen, I also posted another example. That is this one. Okay? Then, I don't know whether it works well or not, but let's do it. Okay? Then, what we want to do is say 1, 0, 0. And then 0, 1, 0, 0. One of them is this, and the other one is 1, 0, 1, 0, 0, and 1, 0, 0, 0. Oops. I'm not getting used to it yet. Okay, I don't know how it goes, okay? I think someone prefers the use of blackboard, okay? I so just want to do the similar thing by this, okay? If this works very good, then this part is also captured by video, okay? So this remains, okay? If I do it on the blackboard, it doesn't remain, okay? So, but if you multiply these two matrices, 1, 0, you goes like this. So this is 0, and then 1, 0, so you get 1 here, and then 0, 0, so the rest of them you get 0. Okay? Then how about the next one? Okay, 0, 1, 1, 0, 0, 1, 1, 0. So the sum is 0. Okay, then again 0 and 0, 0. Okay, so in this particular case, if I just change the order of the product, right? But in one of the case, you got all 0. Okay, and the other one, you got non-zero, right? This type of thing can happen in the matrix calculation. So the order of the product is very important. Okay? So, not last week, okay, on Wednesday, okay, we discussed the identity matrix and the inverse of a matrix. Okay? So identity matrix is, by definition, it's a square matrix I satisfying this condition. Okay? So if you multiply I to any matrix A, then it doesn't change. Okay, so if you multiply I to right hand side or left hand side, it doesn't change this matrix A. So this I is something like 1 in multiplication. Okay, if you deal with numbers, if you multiply 1 to any number, you get the same thing, right? So this identity matrix is something, say, which behaves like 1. Okay? So in Japanese, I always say, ichimodoki, okay? Very close to 1, okay? But not quite, okay, because it's not 1. But we also checked last week, on Wednesday, that side 1, side 2, and side 3, if you take these matrices, okay, then this does the job like this. Okay? So I can be considered as these matrices. Okay? But we just also have to be careful because there may be some other matrix which does the same thing. Okay? But on Wednesday, I also showed a theorem stating that this matrix with this property is unique. Okay? Unique means there is only one such matrix. Okay? But if there is only one such matrix, and if we know one, then that has to be the only one. Right? So from now on, you can consider that this identity matrix is a matrix like this. That is, 1's on the diagonal, 対角線上に1があって、and 0 elsewhere. Okay? Other parts are 0. Okay? So you can consider I is such a matrix. But the, logic we used was first we wanted to consider a matrix I which satisfies this property. Okay? We started from that. But we also found one, and we also show that if there is only one, the unique, then we know that this is the only one. Okay? So in that way we found it. So this I is something like 1 in multiplication. Okay? So in matrix multiplication, this I serves as 1. Okay? So in high school, some of the, second year or third year student, you may have studied, matrix multiplication at high school. In that case, this matrix was denoted by E. Okay, that came from German word ein, that is 1. Okay, but anyhow, I want to stick with this I. Okay, by several reasons, but I don't want to explain it here. Then, so 1 is defined. Okay, so the next step we want to do is we want to find the reciprocal, okay, 1 over I. Okay, since we know 1 over A, we already know 1. So we want to define the inverse of a matrix A. Okay, but since we already have 1, reciprocal 1 over A means, okay, if you multiply that one to A, you get 1. Okay, but you already know 1 in the world of matrices. Okay, so B is called the inverse matrix of A if B behaves like this. That means if you multiply B to A from right and left, okay, the order of multiplication is important. That's why we define it this way. Okay, if you multiply B from right or B from left, you get the one which we just found. Okay? But the I is actually this type of matrix. Okay? So this is the inverse of a matrix. Okay? And we don't know, at this moment, we don't know when the inverse matrix exists for a particular matrix A. Okay? But since by the theory, last time I also introduced that by the theorem we know that if an inverse exists, then that is also unique. Okay, that means there aren't two distinct matrices which behaves like this. Okay, so A is defined, A is given, and if the inverse exists, then that is unique, so we can just name it as something related to A. So that is called A inverse. Okay, we use A inverse instead of 1 over A. Okay. Then we also know, this is also important today, if you have two matrices A and B, okay, suppose both of them are invertible. That means both of them have their inverses, okay, inverse matrix. Then this statement says that AB inverse of AB exists. Okay, if both A and B are invertible, that means inverse matrix exists, then the inverse of AB is equal to B inverse A inverse. Okay, so in English expression, this is called the sock and shoe principle. Okay, that means you know socks and shoes, right? So if you put socks first and then shoes next. Okay, but if you take it off, first you take off shoes and then socks, right? So if you want to reverse the things, you have to also reverse the order. Okay, so in the calculation of numbers like 2 times 3, okay, 2 times 3 is equal to 3 times 2. In that case, you can just change the order. But the in matrix case, as we've seen in the beginning of this class, the order is important. So from this, we can tell that the inverse of AB is equal to B inverse A inverse. But let's check it. Okay, this is the slide I didn't show. I failed to show last time. Okay, so let's check B inverse A inverse. Okay, we want to show that B inverse A inverse is the inverse of AB. That means if you multiply B inverse A inverse from right and also from left, then that becomes I. 1. Okay, let's check the left hand side. Then the place of the brackets of, say, parenthesis. Okay, this is parenthesis, kakko. Okay, parenthesis or bracket. Okay, even if you change the bracket, then the operation of product, say, stays the same. Okay, so if you just change the bracket here, then BB inverse appears, right? BB inverse becomes I. So I doesn't do anything if you multiply I. So from this BB inverse cancels out, and then A inverse cancels out, and you get I. Okay, even if you change the order, you get I. Okay, but if you just multiply A inverse B inverse instead of B inverse A inverse, then you have to first calculate BA inverse part. But BA inverse part, we don't know yet, right? So you cannot cancel BA inverse part, right? So you have to be careful. But from this you can tell that if both A and B are invertible, then the product AB is also invertible, and the inverse of AB is equal to B inverse times A inverse. Okay, and then next I introduce the theorem. Okay, complicated but very important theorem. Okay, this theorem 3.2 just gives you two things. Okay, one of them is a condition when you have the inverse of a matrix. Okay, the condition when the inverse of a matrix exists. Okay, and the other one is when it exists, then how we can find it. Okay, the way to find the inverse of a matrix. So this tells you two things. Okay, so what we do is just write A and I, and they make a bigger matrix. Okay, and then find the reduced row echelon form. And if the left-hand side becomes I, then this A is invertible, and the right-hand side B is the inverse of that matrix. Okay? What if the left-hand side doesn't become I when you reduce to the reduced echelon form? Then this theorem tells you that A is not invertible. Okay? So as I explained on Wednesday, but the A is invertible if and only if the reduced row echelon form of A is I, because the left-hand side, if you just look at the left-hand side, then in order for this matrix A to have an inverse, then the left-hand side becomes I. That means the reduced row echelon form of A is equal to I. In that particular case, the matrix A has its inverse. Otherwise, it does not. Okay, so you get this thing because rank of A is the number of non-zero column, non-zero rows in the reduced row echelon form. Well, this is an example. So we calculated this one. Okay, but firstly, what we want to do is if you want to find the inverse of this matrix, okay, then first write A on the left-hand side. Okay, this is exactly the copy of this matrix, right? And what is on the right-hand side? This is the identity matrix. Diagonal is 1 and 0 elsewhere. Okay, then we want to say use elementary operations to get reduced row echelon form. Okay, let's do it. Okay, then finally we got this last time. Okay, then this is, since the left hand side is I, so the right hand side is, say, name it B, then this B is the inverse of the matrix. Okay, and I briefly explained why this is the case last time. But today I will give you another proof, okay, which is more important. Okay, then today I started with the product exercises of the product of matrices. Okay, so in this case, if you apply 1-2 elementary operation to this matrix, then 1-2 operation means interchanging the first row with the second row. Okay, so you get the second row comes first and the first row comes next. Okay, so we multiply. We did this 1-2 operation to this matrix. Okay, but this is as we saw. This is the same one as you multiply this particular matrix to this matrix. Okay, look at it. Okay, if you want to multiply this matrix with this matrix, okay, since the number of columns of the first matrix is equal to the number of rows in the second matrix of the second matrix, so you can multiply this matrix with this matrix. Okay, then if you multiply this, then first take the first row and then first column. This is 0, 1, 0, 0, 1, 0, so you get 1, 2, 2, 0, 1, 0. So if you multiply if you take the first row, you get the second row. Okay, that is this one. Okay, if you want to get the second row, you multiply with this second row and this column. Okay, so 1, 0, 0, so you get 1, 0, 0, you get 0, 1, 0, 0, you get 1, 1, 0, 0, you get 1, and so on. So as the second row, the first row of the right-hand side matrix appears. So this does the same effect as 1, 2. Okay, so although we just did the elementary operations, but that is the same effect. We get the same effect as you multiply this particular matrix. Okay, and this matrix is called E12 because it is related to 1-2 operation. Okay, 1-2 operation. So we wrote it E12. Okay, E12 multiplied it. Then this is the matrix product. So you can just put it inside. If you just name E1 to be E12 or E1 to be E12, then you got this. Okay, so actually E1, so if you multiply this matrix, then you should get this matrix, right? Because E1i is equal to E1. Okay, but this E1, if you look at this part, right hand side of this one, this is nothing but E1, right? So if you just multiply this matrix on the right hand side, you get E1. This is very natural because just you multiply this matrix. Okay? Then how can we get this E1? Okay? From the operation 1, 2. I will explain it later. But the idea is just apply this 1-2 operation to identity matrix. Okay? You have identity matrix and then apply 1-2. Then you get this matrix, right? You have identity matrix, and if you apply 1-2 elementary operation, then 1-2 means the interchanging the first row and the second row. So you get this matrix, right? So in order to get this particular matrix, what you want to do is apply this elementary operation to identity matrix, and you get it. Okay? Then what about the next one? Next one, we want to apply 3, 1, minus 3. Okay? In order to apply 3, 1, minus 3 to this matrix, you just multiply this matrix. This is the one we have just used. Okay? So this matrix, what does it do? This is the same. This does the same operation as you do this elementary operation. Okay? So if you carefully do it, you get the same thing. Okay? So this matrix is called E3, 1, minus 3 because this matrix does the same job as 3, 1, minus 3. Okay? And since this is wrong, so I just call it E2. Then this one is replaced by E2, so just you get, but if you multiply E2, then just that is multiplying each column. Okay, this matrix. So E2, E1A and E2, E1 appears. Okay, so this one, since we have this one because this is C1 and the first matrix is this one, and you want to multiply this matrix, so you got this. Okay, and similarly, okay, if you do it, then you get this. That means, okay, we just use the elementary operations and we got the reduced echelon form. But that is also can be obtained by multiplying particular matrices from left. Okay, so I just want to define those particular matrices. Okay, they are called elementary matrices. Okay, here I wanted to use E. Okay, instead of I. Okay, for I. E, IC. This is a matrix obtained from IN. IN means identity matrix by performing IC. Okay, so you remember IC, right? IC is multiply. I mean multiply C to row I. Okay, so if you have an identity matrix, then okay, so you have identity matrix, you have ones on the diagonal and 0, 0. Okay? And if you apply IC, okay, we don't know where I is, but suppose somewhere here is ith row. Okay? Then what you get is 1, 1, 1, 1, and then the ith row becomes C and 1. Okay? So this particular matrix is called EIC. Okay? Then next one, EIJ. EIJ is a matrix obtained from IN by performing IJ. Okay? And EIJC is a matrix obtained from IN by performing IJC. Okay, let's look at the example. Okay? 31C. Okay, 31C is first take the identity matrix and then perform this one. Okay, then this is replace the third row by the sum of the third row with C times the first row. Okay, so C times the first row becomes C00. 0. If you add it to the third row, you get this. This is the operation we have just done as an exercise in the beginning of the class. So this is called the E31C. Okay? And similarly, okay, if you multiply this one to XYZ, okay, then that's just we have studied, okay, calculated. This does the same operation, same thing, effect as 31C. Okay. But another important thing is, if you multiply this matrix to this matrix, okay, then what we do is they replace the third row by the sum of the third row with and the C times the first row. C times the first row is C00, right? If you add it together, you get 001. So if you multiply this with this, then you get identity matrix. So you have to calculate the other side as well. But from this, you can tell that E31C inverse, okay, exists, and that is equal to E31 negative C. In general, the inverse of EIJC exists, and that is EIJ minus C. Okay? So I hope you are with me, but you think that it gets very complicated. Okay? So let me explain a little bit more by a different way. Okay? With a different. So you remember that the 31C, okay? 31C is replacing the third row by the sum of the third row with C times row 1. Okay? So you are doing that type of operation. Okay? Then let's think about the way to get back to the original one. Okay? You added the 3 times the first row to the third row. Okay? So in order to get it back, or in order to go back, okay, then what you're going to do is, say, add the minus C times the first row to the third row back again. Then you can get the original one. Okay? So this inverse is doing something like that. Okay? So it says that the inverse operation of 31C is equal to 31 minus C. Inverse operation means if you have done 31C applied to a matrix, okay, then in order to go back, okay, go backwards, what you do is 31 minus C. Okay? So that type of thing is performed by multiplying these matrices from left. Okay? And similarly, this is easy because if you just, by definition, okay, E12 is the matrix obtained by from identity matrix by applying 1-2 operation. Okay? 1-2 operation means interchanging the first row with the second row. Okay? If you interchange the first row with the second row, you get to this one. Right? And this does the job like this. And the inverse of it, if you just say interchange the first row with the second row, and if you do the same thing again, then you get back to the original one. So you get this. Similarly, E3C, if C is not equal to 0, then you get the same thing. And in this particular case, the inverse of 3C is equal to 3 1 over C. Okay? After you multiplied C to the third row, and if you multiply 1 over C to that matrix, then you get the original matrix back, right? So the inverse of E3C is equal to E3 1 over C. Okay? So this is very kind of complicated, okay? But what I wanted to do is, anyhow, this is the original matrix. First we multiply this, okay, by this operation 1, 2, and then by this operation 1, 2, 1, 3, 1 minus 3, you just multiply this matrix, and then this matrix, and then this matrix, and then this matrix, and then this matrix to get this last matrix. Okay? That means from this to this, what we have done is first multiply this matrix, and then multiply this matrix from left, and then multiply this matrix from left again, and then multiply this matrix from left again. Then you obtain this. Okay? Then The first one is E1, 2. The second one is E3, 1 minus 3, and so on. Okay? So what we did is that starting from AI, left-hand side matrix is A. Okay? This is the one we wanted to find the inverse. Okay? Right-hand side is identity matrix. So starting from AI, first multiplied E1, and then E2, and E3, E4, E5, E6. Okay? Since if you multiply something from the left, then that does the things to each column. So you can do the same thing for the first part and the second part. So you can write it in this way. Okay? In fact, you have to have I here, but the I is the identity matrix, so it doesn't do a thing. So I just dropped I. Okay? So you got this. But you know that this is IB. Okay? So, but if you look at this part, then this has to be B, right? This has to be B, right? Okay, are you with me? This has to be B, okay? Then, this E6 up to E1, this part has to be B, okay? So, this complicated part can be written as BA. But if you compare with the first one, BA is equal to I, right? But the objective here was to find the inverse of A. But if you multiply B from left, you got I. So at least you know B is a candidate of that inverse. Okay? Why I say it's still a candidate? Because we also have to check whether AB becomes I or not. Okay? But we know that B is equal to this one. And the BA is equal to I. We know this much. Okay? And the AB equals I and the B is equal to this one. This much we have obtained. Okay? But since E1 to E6 are elementary matrices, okay? So they are invertible, right? So that connected with the elementary operation, it doesn't go forward, but also go backwards, okay? So it has inverse matrices. So if you just write it, then B is equal to a product of elementary matrices, but each of them is invertible. So the product, so is the product. So the product is invertible. But the product, the inverse, B inverse exists. But in order to write out the inverse of this matrix, you have to be careful. Sok and Shu principle, you have to reverse the order, and E1 inverse, E2 inverse, E6 inverse. You have to change the order. But in this way, B inverse can be written in this way. Okay? Then A is equal to AI, but the I part can be, since B inverse is equal to I, so you can write it in this way. But B inverse, but AB was known to be I, B inverse, and the B inverse. Okay, so it may be too quick, but in this way, AB equals I. From this, and the B is equal to this, we got that the B inverse is equal to, A is equal to B inverse. A is equal to B inverse? That's why if you multiply B from left-hand side, then since A is B inverse, so you get that. But this is nothing but AB. So AB is equal to I and B is equal to I. So this matrix B is the inverse matrix. Okay. It's a long proof, okay? But in this way we can prove it. Okay? In this way, you can connect the elementary operations with the matrix operations and the product of inverse of the product with the product of inverses. So let's review. Okay? What we have done is the following. Okay? If you start from a matrix AI, okay? If you want to find the inverse of A, or whether that inverse exists or not, then write A and I. Okay? Then you can find, first you find the reduced row echelon form of that matrix. Okay? And the left-hand side becomes I. then the right hand side B is the inverse of that matrix A. Okay? And if the left hand side is not equal to I, then I didn't explain it clearly, but in that case, the inverse of A does not exist. Okay? So this is the kind of the proof, but this is exactly the same one as I explained using the 3x3 example case. Okay, so this may be too much for you. So if you are interested in the rigorous proof, please look at it. Okay. The next one I just want to mention a little bit is the so-called inverse matrix theorem. Okay. So A is a square matrix. Okay, then the following are logically equivalent. Okay, logically equivalent. I think you remember logically equivalent. Okay, logically equivalent means if the statement I'm not saying that the statement 1, 2, 3, 4, 5 are valid or true. Okay, if the statement 1 is valid or true, then the statement 2 is also true. That is the meaning of the logically equivalent. Okay? So A is invertible. Okay? A is invertible if and only if the following conditions hold. Okay? This is the case, and this is the case, and this is the case, and this is the case. Okay? Firstly, if I take 10 minutes, okay, then I can prove everything to you. Okay? But I don't want to do that much because I want to do some more exercises as well. Okay, but let me briefly explain what this is. Okay, firstly, statement 1. Statement 1 says A is invertible. Okay, but by the theorem we have just studied, we know that A is if I is the reduced row echelon form of A, then that is the case. A has its inverse. Okay? So that means the theorem 3.2 states that 1 is equivalent to 4. Okay? And if it's in that case, okay, as we have seen, A can be written as a product of elementary matrices. Okay? So that is also equivalent to 5. This much is kind of easy. So this is the proof. So if you want to just check it, please look at it. So 1 and the equivalence of 1 and 4, okay, 1 and 4 comes from theorem 3.2. Okay, and also 1 and 4 and 5, okay, also is from theorem 3.2. And the 1 and 2, 1 implies 2 is written here and so on. Okay, so I just want to go ahead and do it. So do the next one. So I just, if you are interested in, please look at the proof. Okay. But I have to say one important corollary. Corollary is the result, okay, obtained directly from the theorem. Okay. In Japanese we call it K. K は系統の K だね。なんかノットに書いて糸か、ね、あれが K、ね、corollary. This is a difficult word for Japanese to pronounce, so I don't want to repeat it again. Okay. So something, okay. Something starts with C. So A and B are, let A and B be square matrices of size Z. Okay. Then the first one says, if AB equals I, okay, by this theorem, we can tell that BA is equal to I. That means if you have two square matrices and you obtain AB equals I, okay, in that case, you don't have to show that BA equals I. Okay, we already know that if you have two matrices and AB equals something, but the BA may not be equal to that matrix, right? But if AB equals I, then BA also equals I. Okay? And this one uses as a proportion 3.4 I just introduced. And if you use it, then you can also show easily that if A is B is invertible, then both A and B are invertible. Okay? And the proof is here. So if you're interested, please check it. Okay? Then since on Wednesday, next Wednesday, we're going to have a quiz. So I just want to get into some of the exercises. Okay? And as you may know, that I'm posting many quizzes on my homepage, but most of them, the solutions are written in Japanese. Okay? So I just picked up some of the exercises here and wrote the solution in English. Okay? So if you go to the homepage, you can get the say quizzes, and also you can get the solution in Japanese. Okay? So if you can read it read Japanese without difficulty, then just go to the site and look at the solutions. Okay? But I just want to explain a little bit in English. Okay? So A is this matrix and B is this matrix and the C is this matrix. Okay? Then compute AB. This is okay, right? So I don't want to repeat it again. Okay? Since I've written the solution, so please check it. Okay? Then B says A is not invertible. This is a little bit difficult. Okay. This is the fact you can use. If you multiply A and B, okay, if you multiply A and B, you got this. But you notice easily that the first column and the third column are equal, right? Then what happens? So if you let, say, B, this part to be B1, B2, B3, okay? Then what you get is A times B1 becomes the first column of the resulting matrix. And A times B3 becomes this. So AB1 equals AB2, AB3. Okay? So you have this. But look at B1 and B3. B1 and B3. These are distinct, different, right? So that means AB1 is this, and AB3 is this. Okay, the same one. Okay, has two solutions. AB1 is this, 2, 2 minus 3, and AB3 is this. That means B1 and B3, both of them are solutions to AX equals 2, 2 minus 3. Okay? Then, if you look at the augmented matrix, the left-hand side, okay, main part, the coefficient matrix cannot be equal to I. Okay? That is one way to explain it. Okay? Please go to the solution of explanation of the solution of system of linear equations, and just check when those solutions become unique, and then you can find it. But here, I'm explaining it in a different way. Okay, so AB1 equals AB3. Okay, what we want to do is to say A is not invertible. We want to show A is not invertible. Okay, so in order to show that A is not invertible, okay, in order to show A is not invertible, we use its contrapositive. Do you remember what contrapositive is? Contrapositive is title. Okay? Or we use the proof by contradiction. Okay? So, let's take proof by contradiction. So, okay, suppose A is invertible. Okay? A is invertible, then A inverse exists. Then multiply A inverse to both sides. Then you get B1 and B3. But B1 is not equal to B3, so you get a contradiction. Okay? So let's you have A, okay, and the B1 is equal to A B3, and this is equal to 2 minus 3. Okay, this is what we have. Okay, then multiply A inverse from left. Okay, then what you have is A inverse AB1 equals A inverse AB3. Right? But A inverse A part becomes I. So this is equal to IB1. This becomes IB3. Okay? But IB1, I is the identity matrix, so that performs like 1. Okay, in the multiplication, it doesn't do anything. So this is 1 and B3. But if you go back here, B1 is 1 minus 1, 0. And B3 is 0, 1, 1. I guess. 0, 1, 1. But these two are not equal. Okay? So starting from the same equal sign, and you got not equal. So you get a contradiction. Oops. あら、どうもやっぱりまだ慣れてないとうまくいきませんね。どうしたらいいのかな、これ。まあいいでしょう。Okay? So, I say that is suppose not. Suppose A inverse exists. Okay? And then multiply the A inverse. Then you got a contradiction. So you can show that the A is not invertible. Okay? So in this way you can show A is not invertible. Okay? So let's go to the next problem. Suppose C is here and C1 is here and C2 is here. Okay? This problem says C2 is obtained by multiplying a matrix T to C1 and from left, okay, and find T and its inverse S. Okay, C2 is obtained by multiplying a matrix T to C1 from left. What is S? S is the one. Okay, it doesn't say anything. You obtained C1 by multiplying S from C, multiplying S to the left. S to C from the left. Okay, so then we want to find it. Okay, so in order to get from here to here, okay, C to C1, what does it do? In order to get from here to here, at least you just use the operation 2, 1, 1. Okay, 2, 1, 1, you will get 0, 0, 1, 2, 1, 1, you get 1, 1, 0. So you get this. Okay, so from S to C1, what you do is 211 operation. Okay? And from C1 to C2, as I written here, it does these things. Okay? So anyhow, please look at the example here. And also, I just wrote some other exercises as well with solutions. Okay? So please look, and you can see some of the English explanations. So please look at it and then prepare for the quiz. Okay? So it's already 12:40, so let's stop here.